Thank you, everyone. So with that introduction, it has defined the runway. Now we are ready to take off with our technical sessions. So the next talk is on Introduction to Linear Classifiers and Key Deep Learning Concepts by Shweta, and that is me. So an informal introduction. I'm Shweta. I'm working as a senior project scientist with Dr. Gupta. It has been more than 5 years now since I joined Translational Bioinformatics Group as a postdoctoral fellow after completing my PhD in genetics from All India Institute of Medical Sciences, New Delhi. So my research interest is exploring, applying, and deploying AI in healthcare for translational outcomes benefiting patients and assisting clinical experts. So starting up with my topic, so my aim for the next half an hour would be to put everything in simple conceptual form, because it is human tendency that if we get to know about the how and why behind anything, we gain confidence and it becomes easier for us to go back, do self-study for deeper understandings. And yes, we definitely want you all to go back, do self-study and explore where AI can be implemented in your area of expertise. So whenever we are talking about ML, we should remember that statistics and mathematics are the two implicit and important team members. All the concepts of ML are backed up by these two. So on that note, I would like to start my presentation. So due to technological advancements and can you see my? So due to technological advancements and increasing digitalization, not only the enormous data is being generated, but the complexity is also added to the data. So that surpasses the human ability to reveal hidden patterns that are very relevant or significant. So what do we need? We need machines or models that can learn from the data and make predictions. So these machine learning models, they are designed to analyze large and complex data sets, discover patterns, make predictions, and automate decision making, which otherwise is extremely challenging to do at large scale. So now the question comes that how machine learning is able to do all these tasks. The answer lies in its ability to create imaginary lines called decision boundaries. The primary goal of these decision boundaries is to differentiate or classify data into distinct categories. Like you can see, this sort of data is linearly separable, whereas this sort of data is little complex and it cannot be linearly separable. So if we make a decision boundary which is linear, then we have certain data points which are misclassified. But if we make a nonlinear boundary, then it's a perfect classifier. So is the case with this example. So in order to classify these or make decision boundaries, we have special algorithms which are known as classifiers. So these classifiers can be of linear, they are of two types, linear classifier and nonlinear classifiers. Linear classifiers, they're suitable when the data has approximately linear relationship, whereas nonlinear classifiers are suitable in case of complex patterns or data. So when it comes to interpretability, because of their simplicity, they are more interpretable and they require lower computational demands in comparison to nonlinear classifiers. So some of the common models in linear classifiers are logistic regression, linear SVM, perceptron, whereas in case of nonlinear classifiers, we have decision trees, random forest, kernel, SVM, and neural networks. So in the coming hands-on session, we will be doing logistic regressions, linear SVM, and perceptron. We learn more about these of the linear classifiers. So what exactly is linear classifier? So these LCs, they are the foundation of many ML models essential for building intelligent systems. Like I mentioned previously, the key idea is to find a linear decision boundary that separates different classes based on the input features. So if we have the decision boundaries, they can be visualized by plotting the data in different dimensions. For example, a linear boundary in 2D data can be viewed as a line, whereas in 3D data, it is viewed as a plane, and in higher dimensional data, it is viewed as a hyperplane. So there are some popular linear classifiers that include support vector machine, logistic regression, and perceptrons. So perceptrons were developed in 1950 to simulate the process of neural learning. Their design was derived from neuron, that is a building block of the brain, and that is why it is able to mimic the way human brain learns. So it was the first algorithm that is capable of learning from data and making predictions. It has 4 main parts: input layers, weights, biases, weighted sum, and then the activation layer. So it takes the perceptron, it takes the input, multiplies it by weight, adds a bias, sums them up, and then passes the result through the activation function, which gives the output in terms of binary, that is 0 or 1. So if we try to understand what weights are all about, these are the special numbers that are assigned to the input features such that they can control the contribution of individual features in terms of making decision boundaries. Or you can say in a very simpler word that weights help us to create decision boundary. Whereas bias, it shifts the decision boundaries, allowing for more flexibility in case of classification. For example, in this, you can see if this is the linear classifier we consider, then there is one point, which is one data point, which is misclassified. But if we shift this linear classifier to this one, then it is a perfect classifier, things have been sorted out. So this shifting from the required, depending upon the complexity of the data, to another is something which is done by bias. Then we have activation function. Activation function is actually the heart of the perceptron, and we will be learning about it in detail shortly, but before that, let us learn about support vector machine, which is another very frequently used linear classifier. So SVM is a powerful linear classification algorithm, and it aims to find a hyperplane that maximizes the margin between different classes. So if you can see in this example, we have option to draw a linear classifier like this, or maybe like this, but what SVM does is, it draws a classifier in this manner so that there is the maximized margin between the two classes. Also, this SVM can be used as both linear as well as non-linear classifiers because of its one main function that is known as kernel function, because it has the ability to project out the data into the higher dimensional space. For example, this can be seen as a non-linear data, but if we pull this data and spreads it in a higher dimensional space, it becomes easier to draw this linear classifier, which was otherwise difficult in this 2D case. So SVM has this quality, it can do all this of complexity related data analysis also. So it is effective for binary as well as multi-class classification tasks, and that is probably one of the main reasons in every published paper, or I should say in most of the published paper, you will find SVM and it's used. So in the next hands-on session, we will build the linear classifier using perceptron and SVM. So now we know about perceptron. What is perceptron? What is neural network? Neural network is when many perceptrons combine together, they form neural network. So it has input layer, it has multiple hidden layers, and it has output layer. So if we have many hidden layers, we call it deep neural network, but if we have few hidden layers, we call it shallow neural network. And if we want to know, this neural network, it works the same way as the perceptron. So if we want to know how a neural network works, we should be aware of how the perceptron works. And this is what we will be doing right now. So like Sir mentioned in the presentation that there are two essential concepts in the context of working of perceptrons, and they are forward propagation and backward propagation. So this forward propagation, it involves during training how data is fed through the network. That is the process of giving input, multiplying it by weights, adding bias, summing up, applying activation function, and getting the final output or prediction. So in this example, like if I give the image of a boat to the model, and then it classifies it as a boat. So this process of giving input and getting the output is called forward propagation. So as previously discussed, weights, they control the features contribution, and the bias, they shift the decision boundary, allowing flexibility. And these two parameters are very important model parameters, and they are adjusted during training to improve accuracy of the model. Then we have activation function, which is the heart, or I should say the deciding authority of the perceptron. So we can think like this activation function as a binary switch for a perceptron. So based on the input data, it either switches on the perceptron or switches off the perceptron. It also adds or you can say non-linearity to the neural network to capture complex pattern like image recognition and natural language processing. So what does that mean? Just for example, if we use the simplest activation function, till now we were getting the answers in terms of 0 or 1. That if one data point is 0, we are calling it as, or we are saying that it lies in class A. And if if the value is 1, we are saying that this data is lying or categorized in class B. But now, with the addition of, But now, when I use this sigmoid function, I have changed the binary 0 and 1 classification to the continuous that extends from 0 and 1. Means that if I take this threshold as 0.5, now I'm saying that anything above 0.5 to 1 will be categorized as class B, and anything below 0.5 to 0 will be classified as class A. And this is what we normally hear prediction scores. And shifting from binary to continuous is very important because it gives us a lot of flexibility, because we know that we are stringent if we are working with 0 and 1. But if we have continuous data during backward propagation, you will see how we are dealing with the data. So we need to have continuous data in order to tweak our models. So there are different types of, different types of activation function, and like sigmoid, ReLU, leaky ReLU, we'll be doing ourselves in the hands-on sessions. So now once the model gives the prediction, there has to be something that should tell us how good or how bad is my model. So because after forward propagation, we have two scenarios. First, the predicted output is equal to actual output. And the second scenario is predicted output is not equal to the actual output. For example, in this image classification, I gave boat, but the machine predicted it to be a truck. So this is wrong. So my machine is not doing good. My machine is a bad performer. So in order to understand this, we have loss function, which is a measure how bad a model is at its job. So it is basically the difference between predicted and actual values. So ideally, loss function should be 0. Predicted value should be equal to actual value. But yes, in real-term scenarios, it is not the case. So we have loss function, and some of them are mean squared errors, cross entropy. We will be doing all these in next 3 days in our practical sessions. So now we have a loss function. The main goal is to minimize the loss function so that model fits the data as best as possible. And this minimization of loss function, this part, it derives the next part of the perceptron, that is backward propagation. This backward propagation, it is responsible for learning from the mistakes, errors made during forward propagation by adjusting the network's weight to minimize the errors. So this process, it involves calculating loss function gradients or derivatives, or in a way we should say it calculates that how each weight which was associated with each input feature in the network contributed to this particular error. So there are certain steps like gradient calculation, in which the gradient is calculated with respect to model parameters, including weights and biases. Then this gradient calculation is backward passed in the network itself. then followed by optimization of these weights and bias with the special dedicated algorithms like gradient descent so that it reduces the loss function. Now this step is repeated again and again during the training data or on the training data to minimize the loss and thereby improving the performance of our model. So the adjustment of the model parameters, that is weights, bias, during the training is very crucial and is an essential part of gradient descent. So what is this gradient descent? So it's a step-by-step process by optimization algorithms that is to make small adjustment in weights and biases in a way to teach the model so that it can reduce the mistakes which it is making. So there are different types of gradient descent like stochastic gradient descent, Adams and RMS prop. And this graph is like inevitable graph whenever you learn, whenever you search gradient descent, this is something which you will see there forever. And in order to understand this graph, I've created one small situation, and before that, the highlighted keywords like optimization algorithms, epochs, mini batches, local minima. So with that situation, we will try to understand these keywords also, because in the next 3 days, you will be hearing and you will be doing a lot with these keywords. So the situation is like, I am blindfolded and standing in the hilly area, and my goal is to reach the lowest point of the terrain or the hill. So I'm clueless because I am blindfolded, I don't know what to do, I'm hopeless. But now if somebody tells me that, okay, I will provide you a guide which will help you or help me to reach the lowest point. So this situation is exactly the situation which we are learning, that is gradient descent. How? The slope of the hill is actually the loss function which we have. The guide is the optimizer algorithm, which will not only tell you the velocity or the direction that you should go in this direction, but it will also tell you the learning rate. So when we have velocity and direction, momentum, we will be learning about momentum or adjusting momentum in our hands-on sessions. Then it also tells me about how big my steps should be. That is, it controls how fast or slow I should progress. Because definitely when I'll take small steps, I'll move slowly, it will take time, but the probability to reach the lowest point accurately will be higher in comparison to larger steps, because it might be the case where I may overshoot and miss the minima or the lowest point. Then comes the epoch, that is, how many times do I want to follow my guide? Each time is equal to 1 epoch. So more epochs, higher the chances to get closer to the lowest point. Then finally, we have minima, that is the lowest point, which is the desired point. So this is what we have done. This is the starting point. This was our desired point. So the gradient descent, it told me not only the direction, but the steps to be taken. It should be big, it should be small. So this learning rate is something steps we are talking about. So if my learning rate is small, I can definitely reach here. But if my learning rate is larger, then I may miss this point and reach to the other end. So this is something, it acts like a guide that tells our machine so as to reach to the local minima, as a result of which, if we have the lowest low function, we will have the maximum performance of our model. So till now we got familiar with optimizers, minima, gradient, learning rate. It can be high, low, epochs, momentum, working of perceptron, neural network, forward propagation, backward propagation, activation function, loss function, linear classifiers, and perceptrons in a very simple manner. So just to summarize, linear classifiers like perceptrons and SVMs are foundational algorithms in machine learning. Neural networks, comprised of multiple perceptrons, utilize forward and backward propagation to make predictions. Forward propagation involves input data, weights, bias, activation function, and output prediction. Backward propagation adjusts weights based on error gradient to improve model performance. Gradient descent optimizes weights and bias to minimize the loss function and improve model accuracy. Thank you. Questions, please.
हेलो मैम, मेरा जो क्वेश्चन है, जो वहाँ पे जो जो परसेप्ट्रॉन कॉन्सेप्ट था, वहाँ पे हम जो कांस्टेंट एज ए मतलब ट्रेनिंग के टाइम कांस्टेंट एक टर्म यूज़ कर रहे हैं, मतलब हाँ, तो उसका उसका मतलब उसका इम्पोर्टेंस क्या है ट्रेनिंग पीरियड के टाइम?
सी कंसेप्चुअली आई मेंशन उसका इम्पोर्टेंस क्या है, जैसे कि आपने इसमें देखा. See, not every, see, these are the classical examples when data is very normal or standard data. But when we work in real world scenario, things are not very simple. They are very complex. So if I take just an example, this is the throat and the cancer, throat cancer, or different types of cancer, one normal and one cancer patient. Things are actually not like that. They are much overlap. So, for example, like you asked what bias is all about, if I have to make a linear classifier, this is the easiest option, and that is all derived through mathematical derivations. So, if I derive, I get this linear classifier, if I don't have bias. But what bias is doing is, it is adding a component, constant component, as a result of which, if you look at this shift, previously it was here, and the classes were misclassified. But now, due to this shift, all the classes are properly classified. So this provides flexibility. And again, this example is very simple. I mean, it's not complex at all. But if you look at the complexity of the data, and their bias is very important. But yes, this shifting of the data in this example, it shows you that what bias is actually doing to our data points, and how it is leading to classifier, which is pretty good enough.
और एक जो सेकंड जो क्वेश्चन है, जब हम ग्रेडियंट डिसेंट जब यूज़ कर रहे हैं, तो उस टाइम दो स्टेप्स है, एक लार्ज स्टेप लेते हैं और एक स्मॉल स्टेप लेते हैं. तो हम कब लार्ज स्टेप लेंगे और कब स्मॉल स्टेप लेंगे, वो हम कैसे डिसाइड करेंगे कि अभी स्मॉल स्टेप लेना है और अभी लार्ज स्टेप लेना है?
Not defined, but there's no hard and fast rule. You have to apply to your data depending upon the complexity or input features. Then you have to, and this is one important parameter when we talk about hyperparameter optimization. Though nahi hote steps, it's a range. Depending upon the data you have to like it's a troubleshoot, it's a hit and try method. कौन सा best करेगा, देख लेते हैं.
अच्छा, मेरे जो मतलब जो लास्ट एक क्वेश्चन है, जो ग्रेडियंट डिसेंट मेथड है, वहाँ पे मतलब बेसिकली देयर आर टू टाइप्स ऑफ ग्रेडियंट डिसेंट मेथड. आई थिंक द फर्स्ट वन इज द बेस्ट ग्रेडियंट डिसेंट मेथड, सेकंड इज द स्टोकेस्टिक ग्रेडियंट डिसेंट मेथड. तो इसमें मतलब मेन इस पे डिफरेंस क्या है, स्टोकेस्टिक्स एंड बैच ग्रेडियंट डिसेंट में?
Yeah, I'll tell you. So, about the gradient descents, the differences between the gradient or the algorithms we will be discussing in details during our practicals. But like you mentioned, there are two. No, they are not two gradient descents. They are more than that. The most frequent one which you hear is stochastic gradient descent and ADAM, but they are more than ADAM prop, RMS prop also, which we are using regularly. So the differences in the algorithms we will be discussing in our hands-on session. We will make you use.
Thank you, ma'am.
Different, and we will be discussing.
Okay, thank you so much.
Ma'am, I just want to ask you regarding the two linear classifiers which you mentioned, SVM and the perceptron. What are the advantages and disadvantages of one over the other? That is
Again, there is no hard and fast rule.
okay. So, like you mentioned, sorry, like you mentioned, I think the kernel trick for where.
SVM normally, we call it as a machine learning technique. And it has been seen, it gives good result in smaller number of sample sets. But smaller, this is in reference to the deep learning. For me, 200 is small. But for you, if you're using deep learning, even 1000 is small. So it depends upon the data sample size. We have to do it and we have to see which is working well on which data. Because yes, there are cases when we get lower number of, like in cancer, the cancer which are most frequent or prevalent, we get good number of data. But yes, in other cases like I work on ophthalmology related problems, it's not very easy. Since last 30 years, we were able to collect just 250 patients. So in those sense, even 250 for that particular disease is too much. I applied SVM on that. It worked fine. It gave me good results. But at times it has been seen if you have some data which is around 250, it is not giving good results. So it depends upon the data. You cannot make any generalized statement that for so much this thing you need to have SVM or you need to have. You have to apply and get the result and then compare.
Okay. And ma'am, just one more question regarding the question which he asked, and you said that for the comparison between like the hyperparameter tuning which you were mentioning, that you have to decide whether you have to take a large step or a small step, how small a step you want to take. So, but is it not that a large step, the disadvantage which you showed was that we might overshoot the minimum when taking a large step, but in case of a smaller step, won't it always be guaranteed that it is, I mean, a smaller step is always guaranteed to be better than large step, right? Because we want most.
So see, when this overshoot, if just suppose if I'm taking the larger steps and I missed my local minima, but still I have not stopped using my gradient descent. There are chances my local minimum, the starting point can be there. So if I reach this point, because I'm using larger steps, my gradient descent is still there. So in the next iteration, it will tell me, you change the direction, you have overshoot. So from there, since I was moving in this direction, from there I'll get back to this direction. So this is why we do it iteratively, repeated process, so that we need to reach local minimum.
Okay, what I meant was, is it not ideal to always take a smaller step, because the smaller step will always be.
I worked on like ophthalmology related this thing. So what we have seen, normally there's a standard for every lab. Like for me particular, if I'm working on deep learning, there's a reference or standard like, okay, I'll start, if the data is new to me, I'll start with this hyperparameters. I started with the hyperparameters in the case which I'm discussing, but I realized that taking smaller steps was giving overfitting. So I moved to a larger site. Then again, yes, there could have been a chances where I would have overshoot, but then again, I am pretty relaxed because I know gradient descent will tell me to come back. But yes, it depends upon the data you have. Maybe if you have the smaller image in terms of the, I'll give you another example. Do we have time, sir?
Yeah, we have already overshot the time, but still you can take that.
So I'll give you two examples. So we are working on histopathology sites, thyroid cancer, which is a very complex situation. And there is another healthcare data in which we have just the ASCT scan of the eye. Tomorrow I'll be talking about that work. So this data and this data, if you compare these data, the thyroid data, the cancer data is very much complex in comparison to this. So when I was doing this data, I found that even learning rate 0.01 was moderate for me. It's a larger step. If you compare 0.0001, it's a larger step. But it was giving me good result. But when I tried on this data, things were very hopeless. So I had to, take another extremely different thing. When I was working at 0.01, now I took 0.0001 just to see, because I tried the
Okay, so, yeah.
See, it depends. What is your aim? आपको time को invest करें. Either you say cost and benefit of them. सब हाँ वो आपको देखना पड़ेगा. अगर हम कैंसर का केस ले रहे हैं, मुझे पॉजिटिव डिटेक्ट होना ही है. So my specificity or sensitivity, whichever you define, वो ज़्यादा ही होनी है. So it has to be our decision कि हम कहाँ पे compromise कर सकते हैं. Things are not very ideal. When you do it, you'll find out कि इतना चीज़ें आसान नहीं है. We just had it in half an hour. Things are very difficult. We took more than 3 years to come to some model. So things are not very easy.
Thank you.
Yeah, please. I think this will be our last question, then we'll have to break for tea because otherwise we'll have less time for hands-on. Please go ahead. Devlina.
Is there any criteria to set the number of epochs for obtaining minimum loss function?
No, there's no exact criteria. We normally start from 30. We have reached to like 45 also. We have reached to 60 also, and we have come back to 10 also. Even 10 gave good results. Depending again, see the answers to all these hyperparameters is the same. There is no hard and fast rule. It depends entirely on the data, what data you are working, the complexity of the data, and the answer is you have to do it, get the result, compare it. This is how you come to the final model, which is going best.
Thank you, ma'am.
Okay, last one.
Hello, ma'am. My question is regarding SVM. You mentioned that in SVM our goal is to maximize the margin. So how do we do that? Like we just maximize the margin to separate the two data set, and we are just shifting the separation line to maximize the margin.
First thing, we are not doing.
Okay.
Second thing, we are using algorithm. SVM is the algorithm. Third thing, everything is derived mathematically. So it's not like we are arbitrarily doing it.
Okay.
So the algorithm inbuilt is such that I showed you an example. The classifier can be drawn like
Yes.
this or this. In that would have been a good classifier.
Yes.
But what it does, it is a part of its algorithm.
Iteration.
Part,
Yeah.
that it takes the middle line and the samples which are at the maximum rate, and then it draws. So it's again an algorithm and it is inbuilt. So that is how it takes it. So that is why it has been labeled as a separate SVM.
Yeah. Okay.
So
Thank
in
you, ma'am.
SVM there are many kernels. Depending on your data set, which kind of kernel is going to perform well will depend only when you apply it. So that is what we call optimization. In each kernel also there will be lots of variables that have to be optimized to see which one of these parameters will make the classifier best. And each classifier has to be evaluated. That's why these machine learning algorithms require a lot of compute power, because you have to iterate over so many parameters again and again. So
Thank you,
this
sir.
will be learning during hands-on.
Thank you, sir.
So I think now we'll break for tea, and after that we'll shift to the hands-on menu, which is towards the right side as we move out.
Before that, I would like Dr. Dinesh to give a token of appreciation to Dr. Shweta ma'am for a wonderful talk on introduction to linear classification.